Okay, so now in this video I would like to talk about the different properties of region of convergence. Okay, so totally there are 6 properties. Let's go right into all the properties of ROC. Now let's look at the first property. The first property, it states that the ROC of any Laplace transform x of s are always the regions that are parallel to the j omega axis. Parallel to the j omega axis. If you look at the previous j omega axis, if you look at the previous videos, you can see that in all the problems you can see that the region of convergence is always parallel to this axis, j omega axis, this y-axis. Always in all the videos you can see that all the problems it is always parallel to the j omega axis. So that is the first property. That is the region of convergence of Laplace transform is always parallel to the y-axis or j-ohm axis. Okay. Now the second property is also very important. It says that the ROC should not contain any poles. It will not contain any poles. This property is very good to check whether your final answer is correct or not. See, for example, the second property means, what is a poles, right? Poles means the values of s at the denominator. Yes, when you equate the equation of the denominator to 0. For example, if I say that if my Laplace transform is of the form n of s by d of s, okay, where n of s means the numerator equation at the numerator side and d of s means the denominator equation at the below. So if I equate d of s equal to 0, and when I find the various roots of this equation, or if I find the various values of s, those values are what we call as the poles of the Laplace transform. Okay, so the second property states that no region of convergence consists of any poles. So that means if I draw a region of convergence on the S-plane, for example, let me assume that this is my region of convergence. Okay, let me assume that this is my region of convergence. Okay, so if this is my region of convergence, then there will not be any poles inside this region. That is a fact. There will never be any poles inside this region. The poles can either come here or here or here or here or anywhere over here, but it will not come inside the ROC. It can sometimes come even on the edge of the ROC. Okay, it can come even on the edge of the ROC, but it will never come inside the region of ROC. If it comes, then there is something wrong with your final answer. This is a very good way of checking if your answer is correct or not. That is, the ROC does not contain any poles. Okay. Now if you look at the third property, if x of t is of finite duration, okay, finite duration, that means x of t is 0 to when it is plus infinity, and x of t is equal to 0 when the t is minus infinity. That is called as finite duration. That means it is limited to a particular value. Okay, it is limited to a particular time. If x of t is a finite duration and absolutely integrable, that means the x of t value, when you integrate it in terms of dt, it will always be a finite value. If x of t is of finite duration and absolutely integrable, then the ROC is the entire S-plane. If you really understood the meaning of this, means this has also another meaning also. If x of t is a finite duration and absolutely integrable, means this is what it means. That is, integral minus infinity to plus infinity magnitude of x of t dt must be a finite value or must be less than infinity. This is also called as the Dirichlet's condition of Fourier transform. Right? So if x of t is of finite duration and it is also absolutely integrable, then the Fourier transform of that signal exists. So if the Fourier transform of that signal exists, then its Laplace transform of that signal also exists. And if the Laplace transform exists, then the ROC of that Laplace transform is the entire S-plane. Or in other words, if the Fourier transform of a signal exists, then the Laplace transform of that same signal also exists, in which its sigma is the entire S plane. So what happens if the signal, or if the Fourier transform of the signal does not exist? Then if the Fourier transform of the signal does not exist, then the Laplace transform of the signal depends on the value of sigma, or depends on the value of sigma, or it depends on the value of real part of S. Understood? This is what is the third property means. That is, if the signal is of finite duration, absolutely integrable, then ROC is the entire S plane. Okay. Now let's look at the fourth property. In the fourth property, it states that if x of t is a right-sided signal, then the ROC is of the form, that is sigma or real part of S greater than A max, where A max is the maximum real part of the any of the poles of x of S. So what the fourth property means is that if you remember the first problem that you did in Laplace transform, if you remember the first problem that you did was that finding the Laplace transform of e raised to minus at into u of t. This is the first problem that you did in this chapter, right? You remember all this. So this is a right-sided graph. If you look at the graph very carefully, this is the graph of e raised to minus at u of t. You see, because u of t is a right-sided signal, the value of u of t is 1 on the right side and it is equal to 0 on the left side. So when I multiply u of t with e raised to minus at, this is the graph I am getting. Okay, it becomes approximately equal to 0 at infinity, right? So this is a right-sided graph, and if you remember the ROC of this graph that you got, if you remember very carefully the ROC that you got, the ROC is somewhat like this. That is, you get ROC, the final answer, as sigma greater than minus A. This is the answer that you got, sigma greater than minus A, or in other words, this is the ROC. If you remember, this is the first problem you did. This is an example of the fourth property. Okay, that is, if a signal is a right-sided signal, that means the left side of the signal is 0, and when the signal is only a right-sided signal, then every time the ROC it will be of the form of sigma greater than some number. This number can be a negative number or positive number or any number. Okay, in our first problem we got this value. If you remember, this is the value that we got, right? So in that case you can compare this property when you are finding an answer. For example, when you do a problem and you see that the given question is a right-sided graph, then you should immediately understand that the answer that you are supposed to get should be in this format. If you don't get this answer in this format, then there's something wrong with your answer. Okay. Now the fifth one is the opposite of the fourth one. Okay. The fifth one says that if the x of t is a left-sided signal, okay, if x of t is a left-sided signal, then the ROC is of the form real part of S less than A minimum, where A minimum is the minimum real part of any of the poles of x of S. This also you have also done. This is the perfect example of the fifth property is your second problem, problem number 2. If you remember, there the value of x of t, here is given as minus e raised to minus at u of minus t. This is the problem that you did, the second problem. If you look at the graph of this looks somewhat like this actually. There's a minus sign over here, so whatever graph you get over here, it will be opposite. So this is the graph you're getting. So because of minus over here, so the amplitude becomes minus. You see, amplitude is minus. So this is how graph you get, something like this you get. Okay, so here in this problem, this is a left side of the graph. You see, left side, the graph is entirely on the left side. That means the value of the signal at the right side is 0. The value of the signal at the right side is 0. So that means in such a graph, then here if you remember, the Laplace transform that you got for this answer is the Laplace and the ROC of the signal. The ROC of the signal you got was in the format of sigma less than minus A. Right? This is the graph that you got. This is the ROC that you got. That is the graph. If this is minus A, then the ROC is in this format. Okay. This is the second problem that you did. This is the answer that you got. So you remember, in that case, then the ROC is always of the format that real part of S is less than a number. This number can be positive number or negative number or any number, but it always be less than a value, some value. That value is nothing but the real part of any of the poles of X of S. Okay. Now the sixth property says that if x of t is on both the positive side of the graph and on the negative side of the graph, that means if x of t is having both on the right side of the graph and on the left side of the graph, then the ROC is of the form a1 less than real part of s less than a2. Okay. This problem that you did was the fifth problem. If you remember that, in the fifth problem, the question was, find the Laplace transform of the signal x of t is equal to e raised to minus b mod t. This is the fifth problem that you did, right? You remember this? In this problem, this can also be written as e raised to bt when t is negative, and e raised to minus bt when t is positive, right? So in this graph, okay, so that means in this graph, if you remember your ROC here, the ROC is like this. Your ROC is like this. You see, it is between two values, one on the left side and the other one is on the right side, and the ROC is between two values. This is the meaning of the sixth property. That is, if a signal is having a graph on the right side and also on the left side, then the ROC is also in the form, it's also between the value a1 and a2. Okay, so that means a1 and a2 can be any number, but the ROC will always be between the two numbers. Okay, so these are the properties of region of convergence. They can sometimes ask this as a theory part, and also but I feel that the main importance of this properties is to check whether your final answer is correct or not. You can apply these properties, you can remember these properties. Okay, check if they are parallel to j omega axis, it should not contain any poles, and if it's a very simple question, then the ROC must be the entire S plane, finite duration and absolutely integrable. If the given question is on the right side, then this should always be seen as your ROC. And if the given question is on the left side of the graph, then this should be your ROC, that is real part less than some number. And if it is a two-sided graph, if it is positive value and negative value, then it should be between these two values. Okay, so now in my next video I am going to talk about the unilateral Laplace transform. Let me just give you a brief introduction about unilateral Laplace. In the next video I'll be explaining in detail, but in this video I just want to give you a very small introduction just to make sure that all of you have really understood the meaning of unilateral Laplace transform. Okay, one important thing that you need to understand about unilateral Laplace transform is that it is a Laplace transform that is applied only for causal signals. That is, unilateral Laplace transform is a Laplace transform that is applied exclusively for causal signals. Okay, the difference between unilateral Laplace transform and ordinary Laplace transform is, you know that for the equation for an ordinary Laplace transform, that is, it is minus infinity to plus infinity x of t into e raised to minus st dt. Okay, this is the ordinary normal Laplace transform equation that you have learned earlier. Let me write L of x of t over here. Okay, this is the ordinary equation of unilateral Laplace transform. Okay, so if you want to define a unilateral Laplace transform, the only difference is that in unilateral Laplace transform the equation is, this is the only difference, that is integral 0 to infinity. The rest is all the same. Integral 0 to infinity x of t e raised to minus infinity. This is the equation of unilateral Laplace transform. Okay, the reason why it is 0 to infinity is because we all know what is a causal signal. A causal signal means all right-sided signals are all causal signals, right? All signals that has a value only at the positive value of time t in this graph. Okay, all signals that come in this right side of the graph are called as causal signals. If you remember the definition of causal signals, the definition of causal signal is that the signal that depends only on the past and the present values of time t. The past and the present values of time t. That means it should not depend on the future values of time t, or it should not be a left-sided graph. That means on the left side of the graph, the value of the causal signal is 0. That means the signal exists only on the right side of the graph. In such a signal, we apply unilateral Laplace transform. Okay. So when I ask you to apply a Laplace transform to a signal, what Laplace transform am I implying? Should I apply the ordinary Laplace transform, or am I implying unilateral Laplace transform? That you should understand the difference between these two. Suppose when I ask you to find the Laplace transform of this signal e raised to minus at. Okay, if I ask you to find the Laplace transform of e raised to minus at given according to some conditions, then this Laplace transform is your normal Laplace transform that you have studied earlier. That is integral minus infinity to plus infinity e raised to minus at into e raised to minus st dt. That's the equation you're supposed to apply. Integral minus infinity to plus infinity. Okay. But suppose if I give you another signal. Okay. Suppose if I giving the signal like this, e raised to minus at into u of t. Okay, then this signal becomes a right-sided signal, or this signal becomes a causal signal. Why? Because it is multiplied with u of t. You all know what is u of t. U of t, the value of u of t is 1 from 0 to infinity, and the value of u of t is 0 from minus infinity to 0. That means u of t is 1 on the right side of the graph. This is u of t. U of t is 1 on the right side of the graph, and it is 0 on the left side of the graph. And it is 0 on the left side of the graph. So this is a right. So when I'm multiplying e raised to minus at with u of t, this turns into a right sided graph. This graph becomes like this. Right? This graph becomes like this. See, there's no signal over here, and the signal is entirely on the right side. So this is called as a causal signal. And if you remember, we have already done this problem, right? So here the Laplace transform that I need to apply over here is called as the unilateral Laplace transform. Of course, by common sense you can understand, because when I am writing over here from minus infinity to plus infinity, then from minus infinity to 0, the value of the signal is 0, right? So the value exists only from 0 to infinity. That's why this equation comes like in this format. This is a one-sided graph, right? Unilateral means, uni means one, lateral means side. So one-sided Laplace transform. So Laplace transform e raised to minus at is nothing but the unilateral Laplace transform. If you remember this, unilateral Laplace transform, you will apply 0 to infinity e raised to minus at u of t into e raised to minus st dt. So we are applying unilateral Laplace transform in this equation. Here you know u of t value is already 1. You don't even have to write this. Okay. So the letter that we use for unilateral Laplace transform is L itself. That you need to understand. L represents the unilateral. There is no other special letter for unilateral. Both for normal Laplace transform and unilateral Laplace transform, the letter that we are using is capital L itself. Okay. So this is the first standard equation you have studied. That is the Laplace transform of e raised to minus at is equal to 1 by s plus a. This is the first Laplace transform, unilateral Laplace transform equation that you have studied. Okay. I just want to give you a brief introduction to unilateral Laplace transform. That's why I have started this. I'll explain more about this, and also the more about the unilateral Laplace transform of standard signals in the coming video. Okay, so the reason, as I said, one of the main advantage of using unilateral Laplace transform is that we can find the standard Laplace transform of standard signals unilateral Laplace transform of standard signals, right, by applying this equation. So all you need to do is simply study these kinds of equations. So like that, more of these standard signals I will be explaining in my coming video.